Greetings all. Good morning. Hope my screen is visible to all of you.
Yes, sir.
Okay. Thank you. So, in our previous session, we discussed about binary search tree algorithms. Binary search tree, finding the smallest, finding the largest, and the search algorithms. So that is what we discussed in our previous session. Okay, finding smallest to finding largest and search algorithm. Okay, so binary search tree means a binary tree which has some properties. That is, the root node will have means all the left subtree left values will be less than the root, and all the right subtree values will be greater than or equal to the root node. Okay, so this is what binary search tree. Okay, in binary search tree, always the leftmost value will be the smallest value, and always the rightmost value will be the largest value. So how to find the smallest recursively and how to find the largest recursively, that we discussed in previous session. And also search algorithm in the given binary search tree, how to locate a value. Okay, so that also we discussed in our previous session. Okay, so in this session we will discuss about the insert operation. Okay, the insert operation we discussed already. Okay, so the theory part we completed. The algorithm part we will discuss in today's session. Okay, algorithm part and the program we will see, and also delete operation we will discuss it. Once this is completed, we will discuss about the general tree. Okay, now binary search tree insert operation. Okay, so the insert function, okay, it adds a new data or new node to the binary search tree. Okay, to insert data, all we need to do is follow the branches to an empty subtree, then insert the new node. It means that we know the rules for binary search tree. Okay, suppose whatever the value you are going to insert, if it is less than the root node, then go to the left of that root and compare with the node that already existing there. Okay, now compare with that node. If it is the new node is again left, less than the that particular left subtree, again traverse in the left side or traverse in the right side. So based on this condition, we have to navigate and find a leaf place. Okay, where we can insert the new node. Okay, it is means in binary search tree we can perform the insert operation only in the leaf node. Okay, it is not possible to insert in between. That is not possible. Always we can perform the insert operation only at the leaf level. Inserting in the middle is not possible in binary search tree. Okay, so the insert takes place at a leaf or leaf-like node. Leaf-like node means a node that has only one null subtree. Okay, if a node is there and it is having a left subtree, means in the right subtree you can insert. Okay, so this is what a binary search tree insert operation. Okay, let us discuss here. Suppose this is the given binary search tree. So 23, 18, 12, 20, 44, 35, 52. So this is the given binary search tree. In this, if we are planning to insert 19, means first we need to compare 19 with 23. Okay, so 19 is less than 23. So go to the left subtree. Compare 19 with 18. Okay, 19 is greater than 18. So traverse right subtree. Okay, again compare 19 with 20. 19 is less than 20. So left subtree. Here, left of 20, we need to insert the new node 19. Okay, see here, 19 inserted in this place. Suppose if you want to insert 38 in this binary search tree. Okay, after inserting 19 in the same binary search tree, if we are planning to insert 38, then what to do? Okay, compare 38 with 23. 38 is greater than 23. So traverse right. Compare 38 with 44. Okay, 38 is less than 44. So traverse 35. Okay, and compare 38 with 35. 38 is greater than 35. So right side of 35, we need to insert 38. So in this way, always the insertion can happen only at the leaf level. Okay, it is not possible. Suppose here 44 is there, means between 44 and 23, it is not possible to perform any insert operation. It is not valid. Okay, always the insert operation in binary search tree will happen at the leaf level. Okay, please keep it in your mind. Okay, and the algorithm. Okay, whenever we are finding a leaf or empty place, in that empty place we need to assign the new node. So this is the add operation. Add operation, we are getting the root node and also new node. Okay, suppose if the pointer where we are looking is empty, in that place we are assigning the new node and returning the address of the new node. Okay, and else means if this is not the case, means okay, if new node is less than root, recursively we are calling left subtree and a new node. We need to insert the new node in the left subtree. Else in the right subtree we need to insert. Okay, else we need to insert in the right subtree. Okay, if it is not less than if it is greater than and equal, in both cases we need to traverse in the right subtree. Okay, so less than means left subtree, greater than means the right subtree. Now see here, how recursively this insertion will happen. Let us check it. Okay, first means the same concept what we discussed earlier. Okay, so the same concept once again in this picture it is illustrated. Okay, so we are taking 19. So new node is less than root. Okay, this is the new node and it is less than root. So left, we need to traverse left. Okay, so root left comma new node is passed recursively called to the function. Okay, now again new node is greater than root, that is 19 is greater than 12. So recursively send the right of 12 to the add function. What is the right of 12? It is null. So it is null means it will come to this place, this if condition. Okay, so 12's right, okay, comma new node. Both pointers will be passed to the recursive call. That is a 12's right, okay, right of 12 and a new node. This recursive call will go to the add function. Okay, and since 12's right is empty, the new node will be assigned to root. Okay, new node will be assigned to root. Means what actually here root is a 12's right. So 12's right will be assigned to new node and it will be returned. So it will recursively send back to the previous recursive call. Okay, so the 19 will be assigned right of 12. Okay, so this is a recursive explanation. Okay, this is the function. Okay, so the C code implementation for the binary search tree. Okay, let us check the code. So this file name is tree3.c. Okay, in tree 2 we performed the pre-order, in-order, post-order, and also we implemented the find the smallest to find the largest and the search operation. These three operations we implemented in tree2.c. Okay, in tree3.c I have included that add function and also delete function. Two more functions I have included in the tree3.c along with the pre-order traversal, in-order traversal, post-order traversal, and also find largest, find smallest, and the search operation. Along with these 6 operations in this tree3.c, adding and deleting operations also included. Okay, now see here, this is what add node. Okay, this is what add node function. So I am passing root and also the value to be inserted. Okay, so using this value, I am creating a new node. Okay, using the malloc function, dynamically I am creating a new node, and for that new node data, this value I am assigning. Okay, after assigning the data, the left and right, initially I am making it as a null. Okay, left and right, initially I am making it as a null. Now I am recursively performing the calling operation. So root equal to null. Suppose if root equal to null means root equal to new node and return new node. Okay, and the value is less than root data means root left equal to add node root left comma value. Otherwise root right equal to add node root right comma value. Okay, so when so this function call, suppose if 12's right, okay, if it is a null means it will come to this function. Okay, and 12's right new node will be assigned and that address will be returned. That will come back and stored as a 12's right. That's why this statement here we are giving. Okay, in the recursive call, whatever the new node created, that new node address must be stored in its parents left or right. Okay, so that is what in this operation we are doing. Okay, so this is add node. Okay, and in main function, what are the changes I have created means, okay, earlier in the tree2, in the tree2 function, sorry, in the tree2 program, in the tree2 program, in main function, I have created this n1, node 1, node 2, node 3 values explicitly. Okay, here I am calling the add node function. Okay, first only the root node, whatever the node I am inserting first, only its address I am storing it in root. Okay, and for rest of the nodes I am not storing the values in the root node. Okay, now root equal to add node of 23, the first node inserted, then second node, then third node, fourth node, fifth node, sixth node, and seventh node. All the 7 nodes are inserted in the binary search tree. Okay, now let us call the add function. Okay, after add function, all the in-order, pre-order traversals, everything let us call. Okay, so we are performing first add operation. After that, the traversals, the pre-order traversal, in-order traversal, post-order traversal, then find smallest to find largest, search operation, everything. All these functions we are invoking. Now let us compile the program. See here, the values are inserted successfully, and this is the in-order traversal. So in binary search tree, the in-order traversal will give the ascending order as a result. So 5, 18, 20, 23, 35, 44, and 50 in-order traversal. And find smallest value 5, find largest value 50, and 20. It is available in the binary search tree. 200. It is not in the binary search tree. Okay, so this is what add function. Okay, this is what add function. Okay. Now the next operation is a delete operation. Okay, so class, please listen carefully. The delete operation is very, very important. Okay, so in a binary search tree, how to delete a node? Okay, because most of the time in binary search tree and AVL trees, compared to asking the algorithm or program, they will give some set of values and they will ask you to perform insert operation, delete operation over the binary search tree, and also in the AVL tree. AVL tree we are going to discuss next. Okay, so you should know how to perform the insert operation in binary search tree and a delete operation in the binary search tree manually. Okay, so you should know the step-by-step procedure. So they are giving some set of values means when inserting the first value, how the binary search tree will look like. After inserting the second value, how the binary search tree will look like. After inserting the third value, how the binary search tree will look like. Step by step, you have to draw the binary search tree. In exam, if they are giving some set of values and asking you to draw the binary search tree, insert operation means each step by step, you have to draw and show it. You should not give only the final binary search tree output. Okay, it is not correct. So each step, the binary search tree's growth, you have to explicitly draw and show it. Most of the time, this is what they'll ask it in the exam, because this is very important. Binary search tree, delete, and the AVL tree operations. Okay, if you're understanding the concept, then only you can able to implement it. Okay, in binary search tree delete operation, there are 4 cases available. What are the 4 cases means? Okay, so that is deleting a leaf node. Suppose if your binary search tree is given like this, if you are going to delete a 22 or 20 or 11 or 5 or 27, all these are leaf nodes. We are not, means no need to make any extra effort. Just make the 9s left as a null and delete the 5. Okay, that's it. Okay, so if you're making the roots left as a null and free the leaf node means that is the process we need to delete for the leaf nodes. Okay, so deleting the leaf node is the first case. Okay, and the next case is deleting a node with only one left subtree. Okay, one left subtree is the second case. Okay, in such case, what we need to do means, suppose if we are going to delete 21 means, make 20 as a left of 22 and delete 21. So 20 will go to this place and it means 22's left will become 20 and 21 will be deleted. Okay, so this is the deleting a node with only one left subtree. Okay, only left subtree. The same way, if you're going to delete a node with the right subtree alone means, make the right subtree as a right of the parent node and delete that particular node. So this is the second case. Okay, let us find. Okay, so let us take this example. Suppose if you are going to delete 20 means, okay, 20 having only left subtree. Okay, make 19 as the child of 18 and delete 20. That's it. So this is node with only left subtree. Node with only right subtree means make the right subtree in this place and delete 35. Okay, that's it. In this case also it is simple. So first 3 cases are simple. Deleting the leaf node, you need not worry about any changes. Directly delete the leaf node. Second case, deleting the node with only left subtree. Okay, make the left subtree to that particular root node and delete that particular root. Okay, so if you are going to delete 20 means, make 19 to this place and delete 20. Okay, third case is deleting a node with only right subtree. So move this right subtree to this place and delete 35. So this is third case. The important case is the fourth case. What is the fourth case means? Deleting a node with both left subtree and right subtree. Okay, deleting a node with both the left subtree and right subtree. Okay, how to perform the delete operation? See here, fourth operation. The node to be deleted has 2 subtrees, left subtree and also right subtree. Okay, it is possible to delete a node from the middle of a tree. Okay, but it will create some unbalanced trees. Okay, so the whatever the trees we are creating, it may be it may not follow the binary search tree condition. So to maintain the binary search tree condition, what we need to do means there are 2 ways available. We need to follow any one way. What is the first way is we need to find the largest node in the deleted node's left subtree. If you're going to delete one node, in its left subtree, whatever the largest value available, that largest value you need to copy to the node to be deleted. Okay, then you need to delete the leaf node. Okay, we already know that in a binary search tree, largest value and smallest value will be the leaf nodes. Leftmost leaf node is the smallest value, and rightmost value is the largest value. So smallest value and largest value in a binary search tree will be always leaf node. So move that value to the node to be deleted, then delete that particular leaf node. That is what we need to do. Okay, we need to find the largest node. Okay, in the deleted node to be deleted, it's a left subtree. Then copy the data, then delete the leaf node. Otherwise, find the smallest node from the node to be deleted, it's a right subtree. Copy the data and delete the smallest node. Okay, delete the smallest node. We can follow any one of these steps. It may be confusing. I'll explain with the diagram once again. See here, suppose if 23 is the node we need to delete it. Okay, then in its left subtree, okay, in its left subtree is at 21, 20, 22. From the left subtree, we need to find the largest value. Okay, in the left subtree, what is the largest value? 22 is the largest value. Copy the 22 to this place. Okay, then delete 22. See here, 22 is copied to this place. Okay, and 22 is deleted. 22 is deleted. This is one way. Okay, find the largest from the left subtree. Okay, or find the smallest from the right subtree. Okay, in the right subtree, find the smallest value and store it in the particular node and delete the smallest value. So this is what we need to do in delete operation. Okay, this is what we do it in delete operation. Let us take an example. Okay, suppose if we are going to delete 18, okay, we are going to delete 18, then what we need to do means we need to find the largest in the left subtree. Okay, largest in the left subtree, or smallest in the right subtree. Okay, largest from left subtree means 12 is the largest. So move here and delete 12. The other way, find the smallest in the right subtree. Okay, smallest in the right subtree is 19. Copy the 19 to this place and delete 19. Okay, delete 19. So in this way, we need to perform the delete operation. Okay, in this way, we need to perform the delete operation. Suppose if you are going to delete 23, okay, if you are going to delete 23, then what will be the result of this binary search tree? What are the two values we can move to this 23?
38.
Yes, 38 is one answer. Find the small, not 38. Class, listen here carefully. Find the
20 and 30.
52 and 12.
Can you post it in the chat window? All of you who know the answer, please post it in the chat window. The two values that can be replaced with the root node. Only 3 answers, 4 answers. Okay, I'll repeat once. See here, if you want to delete 23, you have to find the largest value from left subtree or smallest value from the right subtree. Okay, so left subtree and right subtree means left subtree is 18. It is starting with 18. Right subtree is starting with 14. So in 14, you have to find the smallest. Smallest is a leftmost subtree. Okay, leftmost subtree. So leftmost subtree is a 35, not 38. So finding the smallest in this subtree is a 35. 35 is the smallest. Okay. Otherwise, largest are left subtree. Okay. Here left subtree is 18. In this, if you want to find the largest means the rightmost node we need to take. So rightmost node means 20 is the rightmost node, not 19. Okay. So 20 is the largest value for this subtree. Okay. So either 20 or 35 can be replaced with 23. Okay, and after that you have to delete 20 or 35. So deleting 20 or 35 is easy. Why means that it is a node with only one left subtree. This is node with only one right subtree. So 38 will go here, or 19 will go to this place. So this is the result of deleting 23. This is the result of deleting 23. Okay. So yesterday I have given one exercise. Okay, in that exercise, okay, delete, perform the delete operation. That is a delete 80 and delete 14. Okay, delete 80 and delete 14 and show me the result. Yesterday I have given one binary search tree. I asked you to create a binary search tree. In that, perform the operation, delete operation. Okay, 80, 80, you delete it, and 14, the root node you delete it, and show me the result. All of you try to draw it. I'll give 3 minutes time. Yesterday, I had given some set of values to create a binary search tree. In the same exercise, whatever the tree result you got it, in the same tree, try to delete 80 first and create the binary search tree. Okay, after deleting 80. Then from the resulted tree, delete 14, the root node, and show me the result. So two binary search trees you have to create. One after deleting 80 and the second one after deleting 14. Bhargav, can you show your output?
Yes, sir.
So 10 should be in right side of 7, sir.
Thank you. Class, listen here. All of you able to view this tree?
Yes, sir.
Okay.
Yes, sir.
So this is what the output of yesterday's assignment. Okay, yesterday I have given some set of value and I asked you to create binary search tree. So this is the result of that one. Now I asked you to delete 80. Okay, what is this 80? It is having only one left subtree. Okay, in case if you are going to delete a node with only one left subtree, that left subtree you need to move to the 80s place. Okay, and I think Bhargav tried with 77 in this place and 77's left 66 he made. Am I correct, Bhargav?
Yes, sir.
But it is not correct. Okay, 80 is left subtree is 66. So if you are deleting 80, this 66 should come to this place. Okay, that is what we will do when we delete a node with only one left subtree or only one right subtree. Okay, so if you are deleting 80, you should not move 77 here. Okay, when 80 is deleted, 80 having only one left subtree, so 66 must be moved to this place. So it will look like so this is 66.
Sir,
Yes.
in the original diagram, 80 is only the node of the subtree, sir, and the 66 is on left and 70 is on the right, sir.
70 is on right of what?
70 is on right of 80, sir.
How it will be 70 is a right of 80? If that is the tree you created, means that is wrong. Right side of a node must be greater than the node. So 70 is less than
Okay,
80.
okay. Yes, sir, understand. Sorry, sir.
Correct. Now this is the means this is the BS tree we will get after deleting 80. So 33, 56, 66 and 70. Okay, right of 66 is 70. We are not doing any changes in that. Okay, we are deleting 80 and directly moving the 66 to the place of 80. So 66 will go to means the 80's place and the 66 right is it is 70. Earlier also it is 70, now also it is 70. No change in that. Okay, so this is after deleting 80. Now we need to delete 14. Okay, to delete 14, we need to take largest of left subtree, okay, or smallest of right subtree. Okay, so smallest of right subtree is what? For 14, right subtree is what?
23.
23 is the right subtree. For this 23 is the right subtree, means in this, what is the smallest value?
We have only one right.
23.
34. 20.
Because there is no left subtree. Okay, in that case, the root is the smallest value. Okay, so 23 is the smallest. Okay, so 23 we need to keep it here. Okay, and 23 right is a 33, 33 right is a 56, 56 right is 66, and 66 right is 70. Okay, that is one case. The other case is largest of a left subtree. What is the 14's left subtree? 7. Okay, for this subtree, okay, for this entire subtree, what is the largest value?
10.
10. So copy the 10 to this place over. So 10, left side is a 7, right side is a 23, 30, 56, 66, 70. Okay, both are correct. Because when you are going to delete a node with both children, okay, so both subtree, okay, delete a node with both subtree. In such case, we can follow two options. Okay, that is finding the largest in the left subtree, copy the content to the node to be deleted and delete the leaf node, or find the smallest in the right subtree, copy it to the root node and delete that particular node. Okay, delete the particular node. Both are correct. So the output will be either 10, this is a 7, and then here 23, then 33, then 56, and so on. Okay, and so on, the same. Okay, or 23, okay, left is a 7, and then right is a 10. Okay, otherwise 23, sorry 33, right side is a 33, then 56, then 66, and then 70, and then 70. That's it. over. So this is also correct and this is also correct. Okay, in delete operation, if you are going to delete a node 14 with both subtrees, we have 7 and 23. For 14, both the subtrees are present. Okay, so 7 and 23. In such case, okay, either we can follow this or we can follow this. Both are correct. Okay, so this is how we need to implement the delete operation. Please practice it. It is very, 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 very important. Okay, delete operation of a binary search tree. If a set of value is given to you, how to create a binary search tree from the given set of values and how to perform the delete operation. Okay, means if they are asking you to delete two values, means first you need to delete one value and create binary search tree. Then from the result, start deleting the second value and create binary search tree. Okay, here I asked you to create 80 and 14. Okay, don't directly delete 80 and 14 and create one single binary search tree. Okay, sometimes it will give wrong result. So first, whatever the value they are asking you to delete it first and show the resulted binary search tree. Then from the resulted binary search tree, start deleting the second value and show the result. So this is how you have to proceed. Okay, if you have any doubt in this binary search tree delete and insert operation, please post it in the chat window. Now let us go to the algorithm part. Okay. See here in algorithm, okay, if it is a empty tree means a return false. Okay, nothing to be deleted. If a key to be deleted is a less than root, okay, we need to find the search. Okay, we need to locate the key to be deleted. Delete key. If this is the key value we need to delete, means where it exists, that we need to perform the searching. Okay, for searching we already have algorithm and code. Okay. For binary search tree, we already have a algorithm. Okay, if target key is less than root, search left subtree. If target key is greater than root, search right subtree. The same logic in the delete also we are going to use. Okay, see here in the delete, what is the first logic? Okay, value is less than root, value is key value is less than root means left subtree searching. Value is greater than root means right subtree searching. Okay, so this is for locating the node. Okay, this is for locating the node. Okay, if it is not less than and if it is not greater than, what is the meaning?
Equals.
Equals. So that is what else part. Once you identified the key, what we need to do, that is what else part. So in else part, what we are doing means we are checking whether it has a left subtree alone or right subtree alone or both the subtrees. So if no left subtree, it means that it is having only one right subtree. So make the right subtree to the root return true. Else, if not right subtree, then make the left subtree as a root and return true. So these two cases, if it is having only left subtree or only right subtree, okay. Then the third case, suppose if it is having both the subtrees, node to be deleted, not a leaf, and also it is having both the subtrees. Okay, in such case, what we need to do, either we need to find the largest or smallest. So save the root to delete node and set largest to find largest. Okay, find largest and find smallest. That algorithm that we already implemented in the previous session. We discussed the finding the largest and finding the smallest. So we are calling that algorithm here, find largest or find smallest. Okay, find smallest means right subtree, find largest means left subtree. Okay, then move the data in the largest. Okay, whatever the value we identified as the largest, okay, that data to the delete node. Then return delete BST of left subtree of the root, okay, and key of the largest. Okay, in the left subtree, the largest value we need to delete it. So actually we are not deleting the node with the two subtrees. Okay, we are finding the largest or smallest and copying the content, and actually we are deleting either leaf node or a node with only left subtree or a node with only right subtree. Whenever we are trying to delete a node with both the subtrees, okay, in that particular place, actually what we are doing means we are deleting either a leaf node or a node with the left subtree or a node with the right subtree. That is what we are actually implementing at the end of the last case. Okay, that is what this return delete BST. Okay, that is what this case. Okay, after performing the copying operation, this recursive call is to actually delete the leaf node. Okay, because the content we already copied it to the node to be deleted. So that now the leaf node must be deleted. So that is what we are doing it here. Okay, so this is the algorithm for delete operation. Okay, now let us see the code. See here, this is the code for delete node. We are getting the root and also the value to be deleted. If a root equal to null means return root, because the tree is empty or the particular leaf is empty. Okay, and if value is less than root, okay, then root left equal to delete node, greater than means root right equal to delete node. Okay, else if root left equal to null means free the root, return temp. Root right equal to null means free the root and return temp. Otherwise minimum value node. Okay, so this minimum value node we created as a separate function, minimum value node. Okay, so actually here find a min, find the smallest. This function we created using a recursive call. Okay, the same logic means the same output. Okay, this output of this one and output of this function both are same, minimum value node. Okay, here we are using while loop. We already know that any recursive program can be implemented using any iterative statement can be implemented using recursion. So this iteration is implemented as a recursion in this function. Okay, so here in min value we are using while loop to find the smallest node. Okay, and once we identified the minimum value node, we are storing it in temp and we are performing the copying operation. Okay, temp data to root data, and then we are deleting the temp. Okay, whatever the node we copied. Okay, so that node must be deleted from the right subtree of the root. So that is what this function, particular function call, it is implementing. Okay, now see here, I am deleting 20. Okay, so let us comment all other operations. So after adding all the values, I am printing the result in the in-order traversal. Then I am performing the delete operation of 20, and again I am printing in-order traversal. Okay, after delete. Okay, see here, first it is inserting all the values 5, 18, 20, 23, 35, 44, and 50. So after deleting of 20, the result 5, 18, 23, 35, 44, and 50. Okay, 20 is missing. Okay, so this is what the delete operation. Okay, and from this binary search tree point of view, okay, most of the functions are implemented using recursion. Okay, find min, find max, find the smallest and find largest. You can implement using recursion, and also you can implement using while loop also. Okay, so while loop code, just I'll implement once. Here I have converted the find smallest value using iteration. Instead of recursion, I am using iteration. So smallest value in your binary search tree is a leftmost value. So we need to find the leftmost value. So root equal to root, like that. Recursively we are moving to the, we are finding the leftmost node in a binary search tree. Once it is identified, its data, I am printing it here. Okay, let's take the smallest value. Smallest value. Okay. Okay. Now see here, smallest value is a 5. Okay. Using recursion also we can implement, using iteration also we can implement it. So this is a recursive implementation and this is iterative implementation. Both are valid. Okay. If in exam they are not explicitly asking you to implement using recursion or iteration, you can write any. Okay. Both are valid. The same way, finding the largest means while root right not equal to null, root equal to root right, until we find a node which is not having a right subtree. Okay, which is not having a right subtree. It is the rightmost node in a binary search tree. So until root right not equal to null, root equal to root right, like that we need to iterate and find the rightmost value, that is the largest value. So this is binary search tree insertion and delete operation. Today we discussed that. Okay, if you have any doubt, please post it now. Okay, in the next session we will discuss about the general tree.